Hello student. Today I will discuss about each and every element of basic feedback structure. So let's start our discussion. If we want to regulate the value of system output, here the system output is y of t. So if we want to regulate the value of system output y of t around a desired point or a desired region, what we do is that we give what is called as a reference input, which is denoted by r of t. We measure this output and then feed it back and compare the value of output with that of the reference input, and we get an error e of t. Error is the basically difference between desired value of the output and the actual output that we are obtaining each and every instant of time. So we pass this error through an element which is called a controller, which then calculate what should be the input that need to be provided to the system. So that I can follow the desired output r of t. In other words, controller is a block that takes an error between what is desired and what is actually obtained, and then calculate what should be the corresponding input that needs to be provided to the system. So when the controller calculates the system input and the provided to the same the function u of t is then called as controlled input. So this is the broad visualization of a closed loop control system with feedback. This is called as negative feedback. The reason why it is called negative feedback is because the summing junction where we are having this, we are comparing the reference input and output, and we are essentially taking the difference of r of t minus y of t. So it is called as negative feedback. Now come to the next slide. To understand the basic feedback structure, we consider this type of structure, where the common signal or reference input is r of t, the desired value of the control variable is y of t. This signal has the same unit as the control variable, but may or may not exist as an actual physical quantity. The upper path wherein go from the controller to the system and then to the output, what is called this path is called forward path. In feedback control structure, this path where in go from the controller to the system and then to the output, this path is called forward path. This path and the downward path, this path where in the essentially give the measurement of output back to the summing junction, so that we can calculate the error which then goes to the controller, is called as a feedback path. And in this feedback path, typically one essentially can have other dynamically components which may need to be modeled depend on what we do the system. So for example, I typically would use a sensor to measure the system output. Then a sensor is used to measure the system output, and one may need to take into the dynamic of the system that is used. So what do we mean? by sensor dynamic? Let's say we essentially control the temperature. Let's say we take an example, we want to control the temperature of a room. Then what can happen is it, if we use a temperature sensor to measure the temperature of air in a room, that sensor may have a own response characteristics. In other words, if I use sensor to measure the temperature at this instant of time, it may not show the temperature value instantaneously. So the correct value of this at this instant of time may be showed after a certain response time, which need to be characterized by what is called as sensor dynamics. Now the question we need to ask ourselves, if we design a closed loop control system, is that what is the time scale of the sensor response with regards to the time scale of the system response. See, for example, system response at a second, and if I have a sensor which can provide accurate measurement in a matter of millisecond, then I may not need to really worry about the sensor dynamics. On the other hand, if a system response at matter of second and sensor also has a corresponding response of time in the order of second, then I may need to incorporate the effect of sensor dynamics. So typically sensor dynamic may come into picture when we essentially consider the feedback path, and by analogy and correspondingly an additional component called the actuator comes into this forward path. So controller calculates the control input and then provides the control input to the system, but we need some elements to physically realize this control input. So let me give an example. Let me give an example. We consider where we want to essentially drive a car autonomously. So let us consider the task of steering of the car. So the angle which are providing to steering wheel is the input to the system, and the orientation of the car can be considered the output from the system. Now if I want to certain orientation for the car, then I design a controller to calculate what should be the steering wheel input that should be provided each and every instant of time. Now, how do I realize a practice may input a motor on steering or linkage to essentially rotate them by a desired angle. Now let's say at the instant of time I want the steering, let's say steering column and linkage rotated by 45 degree, by an angle 45 degree. Now the thing is whether I achieve this 45 degree steering angle instantaneously. The answer may be most probably not. Let's say the use of motor to rotate the steering column, if I give a command now, if I may take some time before which the steering column may be actually rotated by the control input at an angle of 45 degree. So that attribute needs to be characterized by what is called as a actuator dynamic. So actuator dynamic essentially incorporated the dynamics of actuator, the response characteristics of actuator, that is essentially take the controller's control input and realize it in the physical world. So that's why actuator dynamics came into play. So the actuator elements block consists of devices that develop enough torque, pressure or heat, etc. to influence the system variable under control. Thus, the actuator elements are the muscle of a control system, while the control function element are the brain. So, the actuator and the controlled process itself are power handling devices. In a large number of practical situations, the controlled process and the actuator together are treated as a single subsystem. This is because of loading effects. Single subsystem means plant. This is because of loading effects. So the structure shown in this figure defines the basic types of signal and components necessary for the description of any feedback control system. However, it must be adapted to the needs of each specific design. Thank you, student.